Hello, students, and welcome. Today, we are going to break down a very important topic in organic chemistry, one that is a favorite in board exams, the chemical reactions of diazonium salts.
Have you ever looked at the brilliant oranges, reds, and yellows in our clothes and just wondered, how are they made? Well, the answer actually lies in some very clever chemistry, which involves a special super-reactive molecule. And that is exactly what we are going to explore today.
So here is our plan for this session. We'll start by understanding a common problem in aromatic synthesis. Then I'll introduce you to the solution, what I like to call the diazonium master key. We'll see why this key works so well, use a simple analogy to make it easy to remember, look at all the new reactions it unlocks, and finally understand why this chemistry is so important in the real world.
Okay, let's begin with the challenge that chemists often face. You see, when you have an amino group that's minus NH2 attached to an aromatic ring, like an aniline, you can't just easily swap it out for other useful groups like chlorine or bromine or cyanide. The usual methods just don't work. This means we need a smarter way, a clever workaround to get the job done.
And what is this clever workaround, you ask? Well, it is the formation of a diazonium salt. This molecule acts like a master key. It's a highly reactive temporary intermediate that unlocks the door to a huge range of aromatic compounds that were previously almost impossible to create.
So, what is a diazonium salt, really? Well, at the simplest level, don't think of it as a final product. Instead, think of it as a temporary gateway. It's a stepping stone that we create from an amine, use very quickly, and then it transforms into something much more stable and useful.
To really understand its reactivity, just imagine this. Think of the aromatic ring as a car, and the diazonium group, the N2+, is a very, very unstable passenger in that car. This passenger is so eager to jump out that it creates an opportunity for someone else to quickly take its place. It's this extreme reactivity that makes it so incredibly useful for us.
But why? Why is this passenger so unstable? And why does this whole strategy work so well? Well, the secret is in a concept called a leaving group. So here's what's really happening at the molecular level. The entire magic of diazonium chemistry, all of it, comes down to one simple fact. The diazonium group, N2+, is one of the best leaving groups in all of organic chemistry. It is just extremely eager to leave the aromatic ring. And why is it so desperate to leave? Because when it detaches from the ring, it forms dinitrogen gas, N2. And nitrogen gas is an incredibly stable molecule. It literally bubbles out of the reaction mixture, and this escape is what drives the reaction forward so powerfully, making it basically irreversible. Remember this, the formation of stable nitrogen gas is the real driving force here. Now, for your exams, here is the formal definition you should remember. A diazonium salt has the general formula Rn2 plus X minus. Its reactivity comes from two things, the high electrophilicity of the diazonium group and, as we just discussed, the ease with which it is lost as stable N2 gas. And a very crucial point for practicals and theory. These salts are so unstable, they must always be prepared and used in the cold, typically between 0 to 5 degrees Celsius.
To make this whole process really easy to remember for life, let's use another very simple analogy. Just think of these reactions as a game of musical chairs that is happening at a molecular level.
So how does this game work? Well, step 1. The diazonium group on the aromatic ring, that is our unstable chair. It's not meant to be there for a long time. Step 2, various other molecules, the nucleophiles, like maybe chloride ions, are the players who are circling this chair. And finally, step 3, when the conditions are right, one player quickly comes and sits on the chair, and the chair itself, the N2 group, is removed from the game as it escapes as a gas. It's that simple, right?
Okay, so now that we have our master key, let's see which doors it can actually unlock. This diazonium intermediate makes a whole range of new reactions possible, transforming a simple amine into a wide variety of very useful products.
For all the examples that we are about to see, our starting point will be this molecule, the benzene diazonium ion. This is formed from aniline, and it will be our highly reactive intermediate for all the transformations that follow.
So let's go back to our musical chairs game. If the player is a chloride ion, we use a copper 1 salt as a catalyst. This reaction has a very famous name, the Sandmeyer reaction. Please note this down, it's very important for your exams.
The copper catalyst helps the chloride ion to replace the diazonium group, the N2 leaves as a gas, and our final product is chlorobenzene. See? We have successfully replaced an amino group with a chlorine atom.
Now, what if we play the game a little differently? What if the player is another aromatic molecule, like phenol? Well, something fascinating happens. The diazonium group doesn't leave completely. Instead, it acts as a bridge linking the two aromatic rings together. This is called a coupling reaction, and the product is a colorful azo dye. And this brings us right back to our starting question. This is how we get those vibrant colors in our fabric.
This table here is an excellent summary for your revision. Let's quickly go through it. The Sandmeyer reaction lets us add chlorine, bromine, or cyanide. If you just warm the diazonium salt with water, a process called hydrolysis, you get phenol. Coupling with phenol, our aniline produces those amazing azo dyes. And we can even completely remove the group and replace it with hydrogen, using a reducing agent like H3PO2. The versatility is truly amazing, isn't it?
So, we've seen the chemistry, but why should we care? Why does all of this matter outside the textbook? Well, this chemistry isn't just an academic exercise. It is the foundation for major industries, from making our clothes colorful to synthesizing life-saving medicines.
Let's just quickly list its key contributions. First, it allows us to create compounds that are very difficult or even impossible to make using other methods. Second, it is the chemical backbone of the entire azo dye industry. Third, it provides a very reliable way to introduce halogens and the important cyanide group onto an aromatic ring. And finally, it gives us a clever way to completely remove an amino group after it has served its purpose in a longer synthesis.
All right, that was quite a bit to take in. So before we finish, let's do a very quick recap of the most important points from this session.
So here are the key takeaways. First, the core idea. Diazonium salts are just unstable temporary intermediates that we use to replace an amino group. Second, the analogy to remember. They work like a game of musical chairs simply because N2 is a fantastic leaving group. And third, the main application. This chemistry is the foundation of the azo dye industry, which adds so much color to our world. I promise you, if you just remember these key points, the core idea, the analogy, and one key application, this topic will feel much, much lighter and easier to handle in your exams.
And finally, I'll leave you with this one thought. The diazonium salt is the unstable key that unlocks a world of stable, colorful, and very useful molecules. It is that temporary, reactive bridge to the vast landscape of aromatic chemistry. Thank you for learning with me today.